Time is 11 o'clock, so let's begin here. So today we will begin Chapter 8. Project number 3 is due on Wednesday at noon, just as a reminder. Are there any questions before we get going here? Okay, before we actually do get into Chapter 8, I do want to mention one thing that may be of interest to some of you. And that is one of the courses that I'm teaching next spring is Stat 875 Categorical Data Analysis. This is an excellent course to take as a follow-up to this particular course here, because about 3/4 of the stuff that we do in 875 are represent extensions to what we do in this particular class. So far in Stat 870, we focus on situations where y has a normal distribution to it. But let's say that we instead have a situation where y is equal to either a success or a failure. How could you represent that? Well, you could say, let's say, a 1 is a success, a 0 is a failure. Well, now, how does that change things in terms of our regression modeling? Obviously, we can't assume that we have a normal distribution because y is binary. And so that's some of the stuff that we talk about in 875. In particular, we focus on, when I discuss this part of the course, we focus on a particular example involving field goal kicking. So in this case, what we want to know, what is the probability that y is equal to 1, probability of success, given a number of particular factors or predictor variables, such as distance, wind speed. Is there some kind of pressure that a field goal kicker is facing when they're actually kicking a field goal? And then once you determine, well, which predictive variables might affect the probability of success, then you want to know, well, how much do they affect the probability of success? So we look at various measures or ways to gauge that information. Another type of variable that we'll look at is to suppose that we have a number of successes out of, let's say, n trials. What probability distribution does that correspond to? Binomial. So in this case, you might have y is equal to 0, 1, 2, all the way up to n. Again, you don't have normally distributed data. Well, so how do you handle that particular kind of situation? That's what we'll talk about. We'll also talk about situations where y is equal to a count. Let's say the number of, for example, people arriving in an airport, or number of cars that are let's say at a stoplight. We'll actually look at 33rd and Holdridge Street, the number of cars that are at that stoplight. If you're familiar with that intersection, you know that there is a fire station at just a little bit north of 33rd and Holdridge. And it just so happens the number, during rush hour, the number of cars can back up and actually block the intersection. Block the fire station so that fire trucks can't get out of the fire station, which obviously is not good. So you might want to know, well, what's the probability that that's going to happen? It's something that we will talk about in my class. And lastly, suppose that y is equal to just some kind of category response, such as, let's say, well, we could do grades. So you have a 5-level response. How do you now do some regression modeling with this kind of a situation? Again, y doesn't have a normal distribution. So, oops, let me actually erase that. So 3/4 of our course discusses these particular topics. 1/4 of the course discusses what I often refer to as traditional categorical methods. For example, in your first stat course, you probably learned about how to find a confidence interval for proportion. And the confidence interval that you probably learned about was something that looked like this. P plus or minus 1 minus alpha divided by 2 quanta from a standard normal times the square root of p times 1 minus p over n, where p is the observed proportion of successes for a sample. Does this interval look familiar? Or you don't care? If it does look familiar, nod your head up and down. Okay, thank you. You probably learned that interval. Well, unless you have it for stat 801, you know that this interval is bad. It doesn't work very well, despite you being taught that in your first stat course. So we'll look at why is it bad, and we'll look at ways that are much better to construct a confidence interval for proportion. Suppose you have a confidence interval for a difference of two proportions. So P1 minus P2 might be the sample estimate. Again, we'll look at how to form a confidence interval in that situation and why the standard methods that are usually taught are not good. And we'll look at, well, what could be better. Many of you probably have heard of a Pearson chi-square test for independence. Sorry, I'm running out of room there. We'll talk about that. What that basically means is, let's say you have two categorical variables, and you can summarize the information in a table-like structure, like a contingency table. How do you test for independence between the two? We'll talk about odds ratios, relative risks. Relative risks are often discussed, for example, in the media. Whenever you see something like, that the probability a person comes down with the disease is reduced by a level amount 5 times if they do one thing versus another. Well, what are they actually measuring in a statistical from a statistical standpoint? So that's what we'll be discussing in this particular class. This happens to be my area of research, so I typically teach this course every spring. The course does usually fill up. It reaches its enrollment cap. In fact, last year it reached its enrollment cap within about 10 days from when students could first register for it. So if this kind of a class is of interest to you, register for it early. Don't put it off because you won't be able to get in the course. The actual grading structure for the course is basically the same as here. We'll have 2 tests, a final, we'll have projects throughout the semester. And lastly, another great reason why you want to take this course is that I'm actually writing a book for this course. It is unfortunately not complete yet. It's about 70% complete. But since it's not complete, that means you don't have to buy it, and I will just give you the PDF of the parts that are complete. So, save $100 or so. Okay, so I just want to give that little plug out there for this course, Stat 875, because I think, again, it's a great course to take as a follow-up to this particular course. I would recommend it to all grad students to take it after they've taken Stat 870. Okay, are there any questions by chance about this?
I have noticed also teach another class, Stat 892.
Yes.
What's that about?
Stat 892 is primarily for stat students who are going on for a PhD. So if you're a stat student going on for a PhD, come talk to me about it. The prerequisites for it are Stat 883 and Stat 970. So if you haven't had those courses, which most of you probably have not, take this course another time. Just don't take it this, I don't think it will be good for you to take it this spring. Other questions? Okay. Yeah.
You mentioned previously about the second test.
Yes.
Is it a solid date for the 13th or exactly?
It will be that week. So I am 95% confident that it will be that week. I'm just not for sure which date it will be yet. A lot of it has to depend upon. A lot of it depends upon project number 4 and you having enough time to be able to complete it so that I can grade it and get it back to you. Any other questions? Okay. Let's see here. So we're starting a new chapter, chapter 8. Okay, so section 8.1 discusses polynomial regression models. We've already discussed this in the context of having, let's say, a quadratic term in our model. But now we're going to discuss it in more detail and also some finer points regarding these kinds of models. So we use the terminology typically first order model to represent a model that just has, let's say, x in the model and it's raised to the first power, first order. And of course, you would just get a straight line with that. A second order model then would also include x squared in the model. Third order model would also have an additional term, or x cubed, and so on. Let's focus though on looking at second order models. That's what we'll primarily do here, but again, you could have third order, you could have fourth order, and so on. Now, just as kind of review in terms of algebra, if similar to what we did with the first order model, we're going to be very interested in the coefficient on this squared term. And that coefficient tells us something about, again, the relationship between x and the expected value of y. If that coefficient's negative, then you have what's often referred to as concave down in terms of what your model looks like. If you have instead the coefficient being positive, then you have what's often referred to as concave up. Now, this x squared obviously is a transformation of x. And because of that, what that can cause is a high correlation between, let's say, x and x squared. If you have this high correlation, then you have potential problems with multicollinearity, which we talked about in the last chapter. And what that can cause problems, especially with, in this particular case, is estimation. You're going to have, and I mentioned this before, when we find this b, in terms of our vector parameter estimates, of course, it's x prime x inverse x prime y. And when you have highly correlated elements or columns, let's say, in your x matrix, you can have problems with finding this inverse. So as a way to lessen this potential problem, sometimes, and I'm going to emphasize sometimes, it can be useful to work with a transformed version of your x. In other words, a mean adjusted version of your x. So you have x minus x bar, so the mean of all your x's. And then call this z, and now your model becomes this, where you have z and z squared in it instead. Note that this beta 0 and this beta 1 will not be the same as your beta 0 and beta 1 that you had previously when you're working with the x's. So don't worry about that. Now, I think that our authors of our book go into, or they're a little bit maybe too concerned about this kind of problem that occurs. In fact, you'll see an example coming up where we have a very large correlation between, let's say, x and x squared, and we have no numerical problems. These software packages are set up to take into account that these problems can occur. And so, in fact, they don't actually use necessarily this exact equation to do the computation. Say, there's various other algorithms that can be used to do this that take into account this problem that can occur. So, anyway, so I think the authors of our book make it a bigger problem than what it really is in actual practical application. But there is a possibility of a problem, and here's a way to get around the problem if needed. Okay, so let's take a look at an example. This is with the NBA guard data set again. Now, when I first introduced this example, you may remember me mentioning this age variable, and that maybe there might be a quadratic effect of age on in terms of a player's performance. Specifically, what I said was something like this. NBA guards that are just starting to play in the NBA, are still maybe learning the game, learning the different facets of playing in the NBA, and dealing with the fact that they have tougher competition than what they had potentially in college. So their performance may not be as good as they are, let's say, a little bit later in their career or mid-career, where now they're used to the game, the speed of the game, and they have some knowledge about how to play the game. And so they might be better, let's say, when they're maybe 28, 29 years old. But then they get to a point where some of their physical abilities decrease with age. And because of that, then as they get into their 30s, late 30s, they might not be as good because of decrease in physical abilities. So if that was true, then you may see something that looks like this as the actual relationship between age and PPM. So notice PPM is higher in the late 20s. So you could say then that my research hypothesis here is that I see some kind of effect like this. And what I'm going to do is, or actually what I've already done, is collect data. And now with this data, I'm going to allow it to help me test my research hypothesis. So let's do that with a regression model. So this potentially could be my model. Expected value of y, where y is ppm, is equal to beta 0 plus beta 1 times x plus beta 2 times x squared, where x is age. Alternatively, what I could do is also represent the model in terms of these mean adjusted values, these z's. So let's estimate these models. First thing I'm going to do, of course, is read in my data set. To estimate the model, we've already done a little bit in Chapter 3, estimating models where we have a quadratic term. So I put in my response, ppm, tilde, age, that's my x, and then age squared has to be represented as I age caret sign 2. It's just the syntax that you need to use with R. You'll see a little bit later on, probably today, why in fact we have to put that I parentheses around the age squared part. Can't just put age squared itself. So I can estimate my model. I summarize the fit in mod.fit1. And my estimated model then is y hat is equal to negative 0.6760 plus 0.0803 times, I'll just say x, minus 0.00144 times x squared. That's my sample model. What if I wanted to now estimate the model that has the mean adjusted predictor variables? Here's one way to do it. There's a number of ways to do it. Now, again, I use my I function, and I say age minus the mean of age. So this gives me my z. I do a similar thing over here to get the squared term as well. So that now when I write out my estimated models, y hat is equal to 0.4398 plus 0.00076 times, let's say, z, minus 0.00144 times z squared. Okay. Now let me jump ahead to page 8.6. Now you might be wondering, well, do interpretations change now with the transform variable versus the non-transform variable? And the answer is no. Here's why. It's exactly the same model, just written a different way. So here's my model written in terms of the z's. Now let's actually put in what the z's are. X minus the mean of the x's, which is 27.53. I show you. I show that on top of page 8.5. And also for z squared, I put in x minus 27.53. If you go through the math so that you just have x and x squared, you get exactly the same model that we had when we were estimating the model without the transform variables. So it's the same model. Same model. Any questions about that? What else? Well, notice here I have a negative coefficient on x squared. So what is that saying to me? Excuse me?
Considering the p-value, not much.
Well, I didn't ask you to consider the p-value yet. Ignore the p-value for now. What does this say? I have a concave down, kind of matching what my research hypothesis was. But of course, once you take a look at the p-value, 0.114. So, there's maybe a little bit of evidence, but not a whole lot, that my research hypothesis is actually true. Let's see. Now you might want to also, before you even look at that t-test that we just did, that p-value, what you might also want to do is look at an overall f-test, just to make an overall conclusion. Is age in a linear or quadratic form important? So, again, just as a review, where do we find the necessary information for the overall f-test? I can come right here. Here's my f-test statistic, corresponding to degrees of freedom, and p-value, 0.2563. Well, that's kind of large. So, there's not sufficient evidence that age in this linear or quadratic form is important. In fact, I would do that kind of a test first before I would even look at then the quadratic effect alone. This gives me an overall measure. For emphasis here, notice that with using the transform variables, you have exactly the same f-test statistic, the same p-value. You have the same t-test p-value as well.
But for linear, we have something different.
Well, you got to be careful here, and we'll talk about this shortly too. You always look at the highest order term in the model. That's what you look at for your interpretation to begin with. Okay. Let's take a look at the correlation between age and age squared. 0.9978. But notice we had no problems estimating our model. So in actual application, would I even work with the transform variables, the mean adjusted variables? No, I wouldn't. That extra part there is to, the transformation is there to help you if you're having problems estimating your model.
How do we know if there is not even
Error message. Also, similar to what we saw in Chapter 7, when you start seeing very large, wrong set of output, sorry, very large in absolute value, and also very large these, then you know you have a problem. So error messages or the same kinds of things that we were seeing in that multiclinary.R program. Let's look at a scatter plot. So there's a scatter plot of my data with the model plotted on it. Of course, I can use the plot function to get the scatter plot. To get the actual model plotted, just use the curve function again. Nothing new there. We can use the predict function. Object equal mod.fit1, so using the untransformed variables I'm using here. New data equal, put a data frame there, age equal x. And remember what curve function does? It just plugs in a whole bunch of values of x, evaluates it, and that's how the plot's drawn, or the curve in that case is drawn. Notice I didn't have to say h squared at all, because R will automatically recognize, oh, h squared is in the model. Okay, you don't need to create a data frame with age and h squared. And so this is what we get. Notice how it's a little concave down, but also notice, it doesn't look like there's a strong quadratic relationship here overall. And this is why we had that t-test result, which was p-value about 0.11, 0.12. Let's talk some more about using the predict function, though, because it can be a little bit tricky at times in these kinds of situations. So very simply, if I want to predict at age equal 20 with my model that doesn't contain the transform variables, that those results are stored in mod.fit1, then I just say new data equal data.frame, age equal 20. There's my predicted value, 0.352. So in fact, we can come back to the plot and look at about it. Let's see. Make sure that that is right. Hold on a second. I want to check something. What was a problem that what's a problem with what I had done here for predicting age at 20? I'm sorry, predicting PPM at age equal 20. Outside of my range. Oh my gosh. Shame on me. Should you do that? No. You can put that on my evaluation. I once predicted outside the range of my data. But probably the reason why I did it, so that I have an excuse, is that, obviously in the NBA now, you can have players who are 19 and 20 years old. It's not unusual. So that's the reason why I did it. Anyway, though. Let me put a note here so that I can change my notes next time. Okay. And to emphasize the matrix calculations here, what I did here was actually, use the matrix calculations. So in other words, what I did was this: I had a 1/3 vector that had 1, 20, and 20 squared in it. I took it times then the vector that had B0, B1, and B2 in it. And of course, I get exactly the same value. Remember, with the matrix calculations, of course, you need to use the percent, asterisk percent, to actually do the matrix multiplication. Let's look at an example using the predict function where you get the wrong answer. So now what I'm going to do is work with the transformed variables. Remember, I saved those results in mod.fit2. And basically use the same code as I did before. New data equal data.frame, age equal 20. Uh-oh. I get 0.44, which is not correct. So what's happening here is that in this context, R is not taking into account this transformation that you specify in your formula argument. It's not taking it into account correctly. or I should say the way you want it to, which would be essentially, here's how I did it in matrix calculations. 120 minus 27.53, 20 minus 27.53 squared times the corresponding B0, B1, and B2 for this particular model. That's what I would want to have happen. And notice how you get exactly the same answer as we did previously. Well, what R is actually doing is this. It's taking the vector 1, 0, 0 times your B vector. Well, why is it doing that? Well, in our formula argument for the LM function, remember this is how we had written the terms of our model. I, age minus mean of age. What R does is this. It substitutes in 20 as you would want, but then when it finds the mean of age, it actually looks at what you have specified in this new data frame, which happens to be only one age and was at 20. So what's the mean of one age at 20? 20. So it actually replaces this with 20. You get 20 minus 20, you get 0. And that's where this is coming from, and that's coming from. So this is just a caution to you that when you're working with these transform variables, you might not necessarily get what you expect the predict function will do if you're not careful. What you can do instead, even though it's a little bit extra code, is actually specify age in there, that mean of age, specify as the mean of MBA $age. So what this tells R is, it says, okay, let's go outside of this function, find my MBA guard data set itself, find the mean of all the ages. So that then when you actually use the predict function itself, it still does that. It still goes to the MBA guard data set to find the mean of age. So just something you gotta be careful about. And you can see I do get that 0.35 there. Are there any questions? Okay. And I give one other way to do it as well on page 810. What about confidence intervals for the expected value of y? Same application of what we've done before. So this would be a nice review too. So predict, object equal mod.fit1, let's say, new data equal data.frame age equal 20. You can do se.fit is equal to true, and what that's going to produce is the square root of the estimated variance of y hat. And then interval equal confidence to get the confidence interval. So, I get to the right place in my notes. So what that means then, at age equal 20, I am 95% confident that the expected value of ppm is between 0.235 and 0.469. If you work with then the transform variables with mod.fit3, of course you get the same result. To do a prediction interval, change confidence to prediction. Okay, questions? So another thing that I want to do with comparing these two different ways to estimate our model, with and without the transform variables, is that, and I'm going to go back here to our original set of output. Now notice how these standard errors, the first two standard errors, are different for the two models. And in fact, for the model that doesn't use the transform variables, you have a higher or larger standard error. In other words, square root of the estimated variance of the corresponding B. So you might be thinking then, well, with this confidence interval for the expected value of y, shouldn't I have a wider interval with using the non-transform variables than with the transform variables? And the answer is no. And this is why. I'm not going to ask you a question about this on a test, but especially for stat students, stat majors, this is something good for you to be able to know how to figure out. And what we can do is that, in this confidence interval formula, y hat sub h plus or minus the value from your t distribution times the square root of the estimated variance of y hat h. So that obviously the estimated variance plays an important role in the width of the interval. So what we can do is actually derive, well, what is that estimated variance in the context of our model? So the way that we do that is, again, we use some of the basics of what we do in statistics that you will learn in a math stat course. And that is, if I want to find the variance of, let's say, A times, let's say, W1 plus B times W2, where W1 and W2 are random variables, A and B are constants. This can be written as A squared times the variance of W1 plus B squared times the variance of W2 plus 2 times AB, the covariance of W1 and W2. So in this particular case, I have 3 random variables, B0, B1, B2. I apply that same kind of methodology to find what my variance looks like. Notice how now I have 3 covariance terms. For the model that includes the mean adjusted data, I can do exactly the same kind of thing. So you can see that these formulas get messy. But what we can do is program these formulas into R. I show how to do this on page 812. I won't go through the details here. And you will see that indeed you get the same square root of the estimated variances. 0.059, which matches what we had in the outputs. So again, if you're a stat student, this is a good exercise to go through to make sure you know how to do this stuff. If you're not a stat student, don't worry about it, because it really takes a math stat course to fully appreciate working with those variances and covariances. Okay. Any questions? Well, so far we've talked about models that have just one predictor variable, x. And we could square it, we can cube it, but what happens if we have more than one predictor variable? What is a second order model in that context? So if we look at number 2 here, we see what it is. I just wrote in terms of the z's. You could do in terms of the x's instead. This is what, if we had 2 predictor variables, z1 and z2, this is what a second order model looks like. So essentially what we're doing is this. Let me write this in here real fast. In addition to the linear terms, which are often referred to as main effects, it's a common term that you often hear people use, especially if you're taking Stat 802. In addition to these linear or main effect terms, we basically look at all pairwise combinations then of Z1 and Z2. So we have Z1 times Z2, but also let's say Z1 times Z1 as well, Z2 times Z2 as well. And so this is what a second order model looks like now with 2 predictor variables. So you should think on your own, well, suppose you have 3 predictor variables. Oh, shoot, I guess I already had that there. If you have 3 predictor variables, well, what happens? It's the same concept. You take the square of the individual variables, and also you look at their corresponding pairwise combinations. These pairwise combinations are often referred to as interactions. I probably briefly mentioned those in the past here. The next section is going to look at them in a lot more detail, what these interactions truly mean. On your own, you should think about, well, what would a third order model with two predictor variables look like as well? Well, it's basically the second order model, and now you work with the cube terms. So three-way interactions and so on. Now, when we work with these kinds of models, there's you can say a hierarchical approach that is almost always followed when fitting these regression models. And that means if we go back up here, this is now with model 1 where we only had one predictor variable. If we go back up here, and if beta 3, let's say, is not equal to 0, we will always leave the quadratic term and also the linear term in the model. We'll always do that. The book gives some justification for why we do that. Some other justification is that if you don't do that, you're going to force particular shapes to your model. If you think of this being graph, particular shapes that may not necessarily be what you want in terms of probably a comparable example is let's say that you remove the intercept term from just a simple linear model, remove the intercept term when it was not significant. What that does, it forces your line to go through the origin. That may or may not be of interest, so that's why we always leave the intercept term in there. In a similar manner, if you were to, let's say, test beta 2 and it's not significant, let's say for some reason you decide to take that out of your model, you're going to force perhaps, let's say, an odd shape to your curve that may not fit your data as well as it should. So we always work with a hierarchical approach. Again, meaning that if this variable is important, we always have the corresponding lower order terms as well. Residual plots. We often look at residual plots in order to make a judgment about, well, is let's say, our variable correctly specified in the model? Well, when you have, let's say, quadratic terms or cubic terms in your model, you only need to look at a residual plot of the residual versus the original variable itself. It's going to give you the same kind of information as if you look at residual versus a squared term or a cubed term and so on. You can try an example on your own to see how you get the same information. Okay, so let's take a look at an example. This is on page 814. And simply MBA guard data set again. We're going to work with now two variables, MPG and age. And it's going to be a full second order model. So I have age times MPG there. And note that I'm using asterisk to mean times. I bring that up because this asterisk in R's terminology, we have to be careful about what it means. You'll see more about that later. I'm also going to have MPG squared and age squared in there. And what I would like to know is this. Is a second order model better to use than a first order model? So a first order model basically would remove the interaction. It would remove the quadratic terms. So is second order model better than a first order model? Again, I can do a hypothesis test for that. Specifically, I can say HO is beta 3 is equal to beta 4 is equal to beta 5 is equal to 0 versus HA not all equal to 0. And how do we test this? Partial F test from the previous chapter. So in that context, then, what I'm going to do is fit a complete model and notice how I specify the terms in the formula argument course, I use this I for H squared and MPG. To get the interaction term, I use age colon MPG. Note that I did not use an asterisk there. I'll explain the difference between a colon and an asterisk in the next section. So I summarize the fit, put it into an object, and this is what it looks like. Just a little quick note here. Notice how I'm getting kind of low p-values with some of these second order terms that are in the model for the t-tests. So you might be starting to think, oh, I bet this partial f-test is also going to be significant. I also estimate then the reduced model, which of course just would have age and MPG in it. And then how do I get then the corresponding information that I need for the partial f-test? The quickest way is to use the ANOVA function, as we saw in the last chapter. So I say ANOVA, my reduced model, comma, my complete model. So you can see on page 816 then how I'm doing the test formally. So the most important thing from this set of output, of course, will be this p-value right there. But let's use a test statistic and also critical value as well. So step one, state your hypothesis. So notice I stated the hypothesis in terms of the model rather than just the parameters themselves. Both ways are fine. Step two, state your test statistic. So SSE for MPG and age, right here. Notice how it says model 1 and model 2. So model 1 is the smaller model, and the RSS stands for residual sums of squares, or what we call SSE. Here is SSE for the complete model. Notice the degrees of freedom is 3. Notice how you see a 3 here. Number of parameters you're testing. Here's my F test statistic, F star, 6.9971. I can then use the QF function to find a quantile from the F distribution, 2.69. So, test statistics greater than the critical value, reject HO. This means at least one of the terms in the second order model is important. Now on a test, unless I ask you for the test statistic or the critical value, again, the quickest way to do this is just to simply look at that p-value. If it's small, reject HO. Any questions? Okay, let's look at some of this stuff in 3 dimensions. We can find the corresponding code here to pull up the plot. So if you remember when we did this in chapter 6, we looked at a particular function called scatter 3D. And this is what the plot then looks like in 3 dimensions. I guess I should mention too, with this code here, notice how I specify my formula argument. Notice I'm not specifying the second order model. I'm just basically saying what's on my z-axis, what's on my x-axis, and what's on my y-axis. And then I say fit equal quadratic to get this second order model. And so this is what the surface looks like here. And I know it can be a little bit difficult to see, but we do see some, looks like maybe some curvature trend that's happening with the points there. And especially when you look at it in the context of the surface itself, it helps you see this trend. But it's not necessarily easy to see. I admit that, but that's what's happening here. And so you might be interested in to look at the same plot, then let's say with both a flat plane, meaning the first order model, and compare it to the second order model as well. And you can do that with this extra part of code here where you say linear and quadratic here. Not for sure why I guess I'm just showing a different way to input the x, y, and z variables here rather than using the formula there. And if I run that code, now you can see the green surface is the second order model. The blue surface or blue plane is the first order model. And you can see, a little bit better too how the green surface is capturing the effects that are actually occurring amongst these, or the trends that you see amongst these points. It's capturing better than the plane itself. So there you go. Any questions?
What about the way that we will get to reducing the model?
Yes.
How do we plot the reduced model, which is not
Yeah.
full quadratic?
Yeah, then it's going to be a lot more difficult. Actually, in the next section, I'll show you a more general way to do this plot, but unfortunately, you're not going to be able to rotate around it. At least in my investigations, I haven't been able to figure out how one could use this same function for some model that might have, let's say, one of the second order terms removed. I haven't been able to figure it out. Maybe there's a way, but I haven't been able to figure it out. Okay, so section 8.2, interaction regression models. So if you had 802, you've talked about interactions a lot. I'm assuming here you have not had set 802 though, because I know some of you have not. And simply, what the interaction allows one to do is to take into account that how one variable affects the response may not be, let's say, independent of some other predictor variable that you have in your model. And in fact, how one predictor variable affects the response may actually be dependent upon a particular level of another predictor variable in your model. When that happens, we have what's called an interaction. These predictor variables interact with one another in how they affect the response. So here's a simple example. Suppose we have a simple first order model with x1 and x2 in it. Now what we first learned in chapter 6 is that if I want to interpret the effect that x1 has on the response, I say for every 1 unit increase in x1, the expected value of y is going to increase by beta 1, given x2 is held constant. But let's say now we want to interpret x1 again, but with the model that has an interaction term in it, x1 times x2. Now notice what happens when you try to do that exact same interpretation. You can't just focus on beta 1 itself. You have to also worry about beta 3 and x2. So for every 1 unit increase in x1, the expected value of y is going to increase by not just beta 1, but beta 3 times x2. And notice since x2 is in there, and that is a predictor variable, the effect that x1 has on the response depends upon, well, what's the level of x3? Is it 1? Is it 2? Is it 100? You can see that how x1 affects the expected value of y is going to be dependent upon the value of x2. And you can do the same kind of interpretation then if you want to interpret what's the effect of x2 on the expected value of y. Well, it depends upon what the value of x1 is. So when we have these extra terms in there, it makes it more difficult to interpret your model. And in fact, if you were to actually plot a model such as this, then the interaction term causes you to, instead of having, let's say, a flat plane in 3D space, instead it's what's often referred to as a twisted plane. It's no longer completely flat. Here's an example of this coming up. So let's consider the model that has MPG, age, and MPG, age interaction in it. And note here, I'm just using this asterisk to mean multiply. Okay, again, we'll talk more about why I'm emphasizing that coming up. So if I want to estimate the model, suppose I put the results into mod.fit.inter, then what I need to do is include the interaction term in there. I estimate the model. Notice the p-value for the interaction term, for the t-test. It's small, suggesting that indeed there is an interaction that's going on. And this is what a plot in 3 dimensions of this model looks like. I'll explain the code coming up. So we have MPG, age, and then the y-axis is basically representing, that should say ppm hat, so the predicted value. And the way that this particular plot's drawn is so that small values are colored in pink, large values are colored in blue to help you in terms of the response, in order to help you see the 3 dimensions. And so we see that for people with high ages, small minutes per game, they have a small ppm hat. But for high ages, high minutes per game, we see that we have a large ppm hat. And we can see there too that this plane is not flat. It's like somebody took a piece of paper like this, here's my flat plane, and kind of twisted it a little bit. Not a full quadratic effect, but kind of twisted it a little bit. And that's what we see there. Now, as I alluded to earlier, unfortunately, the same 3D function that plotting function that we looked at before at least I can't figure out how to graph a model such as this with it. And so what I had to do was use another function to do the 3D plotting called wireframe. This comes from a package in R called Lattice. Lattice allows you to do a variety of different kinds of plots in R beyond those basic plots that you see like with the plot function. And in order to actually use then the corresponding wireframe function, what I needed to do was this. Evaluate my model for a whole bunch of values of age, MPG, and then get the ppm hat. So, for example, I could start at the minimum age, which we know is 22 years old, and the minimum minutes per game, I don't remember what that was, let's say it's 5, find ppm hat. And then, how about at age 22, go to minutes per game of 22, find ppm hat. And do this for all possible values of age and minutes per game. Once I get all this together, then I can say wireframe, let's plot all these ppm hats, plot the ages, plot the minutes per game, and I also have some other various arguments that you can take a look at yourself, such as color equal true, that allows me to colorize what's being on the plot.
What's this? You don't specify the step there. It's automatic or...
What do you mean specify what?
You basically give from lower MPG to high MPG, but you don't specify the step by which it changes. Does it do it automatically or something?
I'm sorry, I'm not for sure what you mean by...
When you do the save XYZ,
yeah,
you basically do, let's say, do age from NBA minimum
okay.
to NBA maximum without giving by.
Yeah, I just skipped over that aspect. I wanted to get to the actual how to do the plot. Now I'm just about to talk about how I did basically a do loop to some respect to get this evaluation. The main thing is I wanted you to realize that this is what I had to do. I had to actually basically create a whole new data frame that evaluates my model, a whole bunch of ages and MPGs. Okay, so how did I get this data frame? That's what I want to talk about next. First of all, I want to find my minimum age and my maximum age in the data set. So we know the minimum age is 22, the maximum age is 37. And so what I like to do is create, a bunch of values of age to evaluate our model at. And have we talked about using a colon in this context before in this class? Does anyone know what's going to happen here when I hit enter? Yeah. It basically allows you to look at all integers between 22 and 37. So this colon, and be careful, this colon is used in a different context to what it was in the formula argument, basically allows you to do this. Sequence, which we have talked about before, sequence from equal 22 to equal 37 by equal 1. Okay, so it's just a little quick shorthand way to do this. Now I need some minutes per game. So minutes per game, the minimum is 4.35. Max is 40.7. And so what I'm going to do here is simply use what's called the floor and ceiling functions so I can get integers to work with. So for example, if I did, make sure I'm doing exactly how I did it here. If I did floor of 4.35, does anyone know what the mathematical floor function is going to do here? It's not rounding. So, maybe some of you have seen this in a math class before. If I do this, this is the actual symbol that's typically used. Does anyone know what that means? 4. So in other words, it just chops off the stuff after the decimal point. Alternatively, what I could do if I did 4.35, sorry, I drew that wrong. Suppose I did this. This is called a ceiling function. Does anyone know what that's going to do? It's going to be 5. So it just takes you up to the, bumps you up to the next integer. So floor and ceiling function. And there are functions in R called floor and ceiling to allow you to do that. So I just wanted to get to integer values. So I have a range of stuff to evaluate at. So for example, let me just highlight this right here. And there we go. Then what I like to do is look at a whole bunch of different combinations of the ages and the minutes per game that I just generated there. And the way I can do that is through a function called span.grid. So, if you're familiar with for loops or do loops, what this essentially does is a for loop or do loop that loops over all the different possible combinations. So, for example, so the first 6 values, here are all my 6 ages and a minutes per game of 4. I do the tail. There's the last minutes per game and those last ages. So you can see there are 608 different combinations. So that we don't lose track of why I'm doing this is because I need to find ppm hat for all those values so I can graph it. So I just say predict object equal mod.fit.enter, new data, there's all those possible combinations. And what I'm going to do is immediately write these ppm hats into my save.xyz data frame. And we might not have looked at this before, but what I can do is put a $sign here, put a ppm.hat there. That automatically creates a new variable in my data frame that contains all these ppm hats. So that, if I were to say this now, you see the ppm hats. So that's how I created my data frame. It's just a matter of getting used to R syntax so that you can do it on your own. There's various options in this wireframe that allow you to change the angle that you're looking at this, because especially for static 3D plots, you often have to change the angle. And so, just emphasize what I did here. There's an argument called aspect, which talks about aspect ratios and plotting. Take a look at the help for that. Learn more about it. When I change the aspect here, you can see I have a different angle of my plot. And you can see the twisting of the plane there. Okay. Suppose that the this t-test for the interaction term, suppose it was non-significant. Suppose I had a high p-value. What would you expect that plot to look like? Would it be a twisted plane? No, it'd probably be just kind of rather flat. Okay, let's talk about some coding in R to get these interactions in our formula argument. What we've talked about so far is that we can use this colon in a formula argument to say, I want an interaction. But there's other ways you can get the model that we're interested in. You just got to get used to the syntax. This can be especially confusing if you're coming from a different software package than ARM. Notice I can say age asterisk MPG. What this means in terms of R's terminology is this, that you want the age and MPG interaction, but you also want the main effects. In other words, age and MPG alone. So these two are equivalent ways of specifying your model in a formula argument. Obviously, the second way, just a little bit less typing. I usually don't do the second way because just for emphasis that indeed I do have this as my actual model. That's just my personal preference. You can do what you want.
What happens if you add the age plus MPG and the absence?
Okay. Thank you for foreshadowing. Well, what happens if you did do that? Well, what R is going to do is say, oh, you've already specified age and MPG there, so I don't need to add another age and MPG to your model. So this code here will work just like these two previous ones. So, this can especially be confusing to a new R user if they see someone use age plus MPG plus age asterisk MPG and think, okay, the way that I specify just an interaction term is with the asterisk. But no, that's not actually correct. Just the interaction term, use the colon. And lastly here, another way to specify this exact same model is to use this syntax. Parentheses age plus MPG caret sign 2. This does not mean take age and MPG and add them together and square them. Instead, this is just a way to say I want age, I want MPG all the way up to a second order model. So you're going to get age, MPG, and then the interaction. For those of you who are familiar with SAS, there's similar, unfortunately I don't remember off the top of my head, there's similar syntax like this that will allow you to do something like this. Yeah, the at symbol, yeah, or the straight line. Yeah. So this is why, since R has this syntax, this is why we can't just use like a caret sign 2 to mean I'm taking a square of a number. And in fact, if you were to actually put in, suppose we just had age, and suppose you did this, ppm tilde age plus age caret sign 2. What do you think R is going to do? It's going to think that it wants all let's say, a second order model. I'm sorry, let me state that again. Got to be careful with my terminology. It's going to say, okay, you want age and all interactions with age in your model. But if you're only putting age here to begin with, well, of course, what do you get? Well, R will think that this is equivalent to ppm tilde age. That's it. So, there you go. You could also have, let's say we had a third variable. What's going to happen here? Age, MPG, and some other variable I call var3. You're going to get age, MPG, var3. You're going to get all pairwise interactions. You're going to get all, well, you get the one three-way interaction. You know,
Do you get? Isn't it already next level?
excuse me?
Isn't it already next level?
What do you mean by next?
Three-way.
Well, you
You did.
yeah, we're just talking about interactions here. And sorry if I might have actually misspoken before we're calling quadratic or cubic or second order model, third order model. We're just talking about interactions here. That's what I was trying to say. What you should do on your own as a simple exercise is go to the MBA GAR data set and try this with 3 different variables and see what you get. And that's how you explore some of this stuff in your own. I mean, obviously I can't, we don't have time to talk about, to go through every single possible combination of the different sets of code. This is where you can simply plug in the code into a formula argument for a data set, for an LM function, and see what it gives you. And that's where you can figure out what's going on. I'm just giving you the basics so that you understand, okay, this is an interaction term, this is how to do a quadratic term, for example, and so on. Okay. If there's ever a problem with the interaction term in terms of having a very high correlation between the interaction term and, let's say, the original variable itself, you can always do a transformation with your data. Okay, I think that gives us takes us to a good stopping point. Are there any questions? Okay, that's it for today.